Thanks, everyone. Today, I'm going to tell you about some recent results that we have, which are all about improving efficiency in secure computation. And if you don't know what secure computation is, don't worry. I will try to do like a 5-minute introduction into secure computation, which has been work for 30 years. But hopefully, in 5 minutes, you will get everything that you need for my talk. Let's see. So what does it mean to compute with private data? So let's try to define what we will be dealing with in this talk. So let's start with Alice and Bob that are often used in crypto talks to describe what we want to do. So in this case, Bob will have a large database. And then Alice would want to submit some queries to this database. For example, she might be interested in all the records that contain information relevant to her. And she would want to retrieve these records, or she would want to execute some more complicated query. So we would want to enable these two parties to achieve this functionality. And then on top of this, we would like to have some security guarantees for the data and the queries involved in this protocol. More specifically, we would like to hide Alice's query from Bob. So this would be private information for Alice. And then on the other hand, we would like to preserve the privacy of Bob's database for anything that's not relevant to Alice's query. So we would like to keep the database that doesn't match the query for Alice private and do not reveal it to Alice. So more specifically, if we want to generalize what kind of guarantees we want to achieve, secure computation, which in general is enabling us to solve situations where there are different parties that want to compute on private data that they have jointly, would like to provide the guarantee that at the end of the execution of this protocol, the parties will not be able to learn anything more about the inputs for this protocol than what they learned from the output they were supposed to receive. So in particular, in this case, Alice was supposed to receive the records that matched, and that's the only thing that she should be able to learn from the execution of this protocol. So this is kind of the 1-minute introduction of what secure computation is. And why do we want to be able to do secure computations? Well, there are many applications where secure computation would give us some useful guarantees. I already mentioned this database search scenario where we have a party that wants to submit queries to another database. There are many settings where different companies are holding complementary data in some sense, and they want to compute jointly on this data. They might want to find the intersection of their users. They might want to authenticate a user against a database of authentication information that they have. They might want to do some machine learning algorithms on this joint data. And in most of these scenarios, the inputs will be sensitive and private for the parties, and we would like to execute a protocol that just enables us to obtain the desired output without revealing anything more about the input. So now that we have defined what is the goal of secure computation, then the next question is whether we can do this, whether we can achieve this. And if we want to summarize the work for the last more than 30 years, the way to summarize it is that we know how to compute securely any function. So in this case, I was giving you the example of the queries over the database, but we actually can come up any function that we want to compute jointly on distributed inputs. We know how to do it with cryptographic protocols. And I'm not going to go into details on how this what is the history of secure computation. But then I want to also answer in 2 sentences the question, how do we do this? How do we achieve this thing? So in general, the recipe for for many of the existing protocols start with step 1, where you take your function that you want to evaluate, and you represent this function as a circuit. You can think of this either as a Boolean or as an arithmetic circuit. And once you have transformed the computation in this manner, the next step is you develop a cryptographic protocol that enables you to evaluate this circuit gate by gate. So there are many different constructions that achieve this in different ways, but the common feature among them is that this evaluation is happening gate by gate. And why do I put emphasis on these 2 steps? Is because I want to look a little bit more carefully on the first step, which says that we first need to convert our function that we will be evaluating into a circuit. And the reason that I want to focus on this is that this will have an implication about the efficiency of such protocols. In particular, if we are using this circuit representation, this would imply linear work for the computation in the size of its inputs. So this is at least linear work in the size of its inputs. And if we go back to this example that we started with, where Bob has a large database and Alice has the small query, this means that if we want to put the whole computation in a circuit, this circuit has to take as input the whole database, and you will end up running at least linear in the size of the database. And this, for most purposes, when we are dealing with large inputs and large databases, when we are not concerned with security, people in practice try to come up with sublinear algorithms. So this overhead that's coming inherently from these types of protocols is a little bit bothersome when we're thinking of whether we can use this on large data. So, but don't worry. We know actually how to improve over this. So we know how to construct protocols that get us better efficiency than this at least linear in the size of our inputs. And this is more or less where the story for this presentation starts. Because for this talk, I will tell you about some of the tools, or how to construct some of the tools that enables us to achieve these protocols that allow us to achieve sublinear efficiency for computations that in the clear are running in sublinear complexity in the size of their inputs. So for the rest of this talk, I will maybe mostly talk about one of these works, which is constructing one of the basic building blocks, which is called Oblivious RAM, that is used in protocols that achieve this sublinear complexity in their computational efficiency. And this is a joint work also with Adria, who is here at the Institute, and several other people that many of them moved from one institution to another. So in this work, we will present a new construction for this primitive Oblivious RAM, which I will define later in the talk, that will allow us to achieve better efficiency for the purposes of specific implementations with new sizes of databases. And then, if I have time, I will also tell you a little bit about another work, which this time uses these Oblivious RAMs as a tool to construct more efficient protocols if we want to execute this type of queries that I was telling you about in the beginning. But now we want to have more expressivity. We want to be able to handle Boolean queries. We don't want just to have exact matches or looking up a particular item in the database. We want to be able to handle these more expressive Boolean queries. So let's see how far we managed to get. OK, so going back to this question of can we do better than this secure computation that uses the circuit model? Well, in general, the way we are used to express computation, or when we write programs, is usually random access machines. So if you look at your description of your program, it consists of instructions that are doing some computation over your inputs. And then from time to time, they also read and write from your memory. So this is a natural model of computation. And in order to escape this linearity in the size of the inputs, this will be the representation of computation that we'll be using to construct secure computation protocols. So we can try to think about the description of the computation that we will be using when we are representing a random access machine. And we can think about the instructions in a program. So these instructions will be either instructions that do a computation on the inputs or the intermediate state, or the instructions that are accessing the memory. So now we have this representation of the computation. And then I already told you that we know how to construct secure computation that can express the functionality as a circuit. Well, what we can think to do is to take each of these instructions that are the description of our program, and we can create the circuit that evaluates each of these instructions. So now we can chain these circuits that are computing each of the steps in our program, and we can obtain a representation for the execution of the whole program. And each of these circuits we can already implement with these existing approaches for secure computation. The problem is that so far what I have described is only the part of the computation that's executing computation instructions. I haven't told you anything about the instructions that are actually touching your memory. So in particular, in the steps that need to read and write from memory, this computation would also have additional inputs which are coming from the memory. And this memory is not described so far in the description of the program instructions. So, well, we can try to think about how to deal with this memory and how to deal with these accesses. And of course, we can take the function that describes the access into memory, and we can write its circuit representation. We can tell you how to represent a circuit that looks into the memory and selects a particular location from this memory. If you write one huge circuit that takes the whole memory, then you're back to the initial problem that you will have to be essentially linear in the size of the memory. Alternatively, you can break it into small circuits that look at separate locations into memory. But then we come up with a different issue for this protocol. And in particular, this issue is related to the fact that now we are revealing the access pattern of the protocol into memory. In particular, the parties who are executing the protocol, or more specifically, the party who is storing the database, will be able to identify the locations that were touched during the execution of the protocol. And this reveals information about the inputs on which you are running your computation. As a simple example, you can think about binary search and the fact that if you are able to look at the access pattern of binary search, you can infer a lot of information about the value for which you are looking in this binary search query. So now, in order to complete this construction for secure computation for RAMs, we need to figure out how to deal with this last problem, which is reading and writing into memory without revealing this access pattern. So here is also the moment to define this main tool that we'll be constructing for the rest of the talk. And this main tool is called Oblivious RAM. And this notion was introduced in '96 by Goldreich and Ostrovsky. And the scenario for which this tool is constructed is the following one. So Bob has a database, and he has outsourced this database into the cloud. And then he wants to access several of the files that he has stored into the cloud. So if he goes ahead and reads different parts of the memory, then the server that's holding the memory will be able to observe the access pattern. So here, the red ones are the ones that have been accessed. And based on this, as we already said, the server can infer a lot of information about what Bob is looking for. So the goal of an Oblivious RAM protocol is to hide this information from the server. So the first property that an Oblivious RAM protocol needs to achieve is what is called access pattern hiding, which says that we want to come up with a protocol that allows Bob to query his database in such a way that if we have a server who is observing what's being touched in the database, any two sequences of accesses into this database that are of equal length should be indistinguishable based on just observing this, what locations in the database have been accessed. So a sequence that reads 10, 50, and 30 should be indistinguishable from a sequence that reads 3 times the same location in the database. And note that just having this requirement, there is a trivial solution for this. Every time you need to access something from the database, just read through the whole database. So to make this problem non-trivial, we need to state the second requirement for such constructions, which is efficiency. And this efficiency requirement says that we want a protocol that has complexity sublinear in the size of your database. And ideally, we really want a solution that's polylogarithmic. So now with these two requirements, this is really the construction that we need to complete our secure computation protocol that I was describing in the previous slide. And let me just give you an example why this RAM computation will be so much better than the one with the circuit. If we go back to our binary search example, if we use the circuit that takes the whole database versus a protocol that executes log-n lookups for the binary search, and then each of the lookups in memory is executed using this Oblivious RAM protocol, we end up on one side with linear complexity in the size of the database, and in the other one, we obtain exponential improvement in the complexity, and we just get a polylogarithmic complexity for the execution. So now that we defined what an oblivious RAM is, there have been several constructions for oblivious RAM for the last maybe 20 years. But largely, we can classify these ORAM constructions in two categories. The first category is, I call them hierarchical constructions, because the way they store and organize the data consists of this hierarchy of levels where the sizes of these levels double as you go down in this hierarchy. The interesting thing about this construction is that the best asymptotic complexity construction is from this flavor. This is the work of Kushilevitz, Liu, and Ostrovsky from 2012. And this is currently the most efficient oblivious RAM construction. Also, this type of hierarchical constructions have a bad worst case scenario. So if you come up with the worst case, you might end up having to do linear work before you answer your next query. But overall, their amortized complexity is still polylogarithmic. On the other hand, the other type of constructions are called tree-based ORAM constructions. So they store the data in this sequence of increasingly smaller trees. And the interesting thing about them is that they don't have worst case scenario. Each query takes exactly the same amount of time. And in practice, they turn out to be much more efficient than the hierarchical-based constructions. The most efficient implementations that we knew before our work were really using this paradigm of tree-based oblivious RAM constructions. So now we know what are the two flavors of ORAM constructions. And going back to the picture of constructing secure computation for RAMs, now we have armed with these ORAM constructions, we can achieve the polylogarithmic complexity or the polylogarithmic overhead over the execution in the clear that we were aiming for. But for the purposes of this talk, I will be really asking a little bit more fine-grained question. In particular, is how expensive will be the two-party computation that is implementing this ORAM access? So now I really care about the size of these circuits that I'll need to construct in order to implement the ORAM access algorithm, and which we will need to run with the existing circuit two-party computation protocols. So I would like to know specifically efficiency in for concrete database sizes and how it scales with different database sizes. And if we want to be even more precise, I would care about the deamortized ORAM complexity. And what I mean by this is that all of these constructions that I listed for you have a preprocessing stage, which is linear in the size of your database. It's executed only once. So you pay this price only once before you start using the oblivious RAM construction. But if you want to be fair and evaluate the efficiency, you really want to deamortize this linear work that you spent up front once you start computing the complexity of your queries. So I would really want to care about taking into account this preprocessing stage. And this actually does matter when we start thinking about the fact that we will be putting this algorithm for ORAM access inside secure computation protocol and the fact that we will need to describe circuits that are implementing this computation. And there was a work in 2015 that actually gave a new construction of Oblivious RAM, which wasn't achieving better asymptotic complexities, but what it was optimizing was the size of the circuits that are used in order to implement these ORAM access algorithms. And they show that in order to achieve better efficiency for secure computation, this is not the same as achieving the best asymptotic efficiency for ORAM. But if we take their numbers and we try to plot the complexity of just doing a linear scan, which is the trivial ORAM that I described for you, this is the line that we get. So it seems that before we start getting advantage from the ORAM construction, which is right around here or here, we need to go to pretty large database sizes. We have to go to database sizes of the order of 2 to the 16th. And there are many interesting applications that deal with databases of smaller sizes. And from this graph, it looks like for any of those database sizes, in practical applications, the linear scan should be the solution of your choice. So for our work, we were bothered by this question because it seemed that ORAM has a lot of potential, and we really want to make it applicable for average or moderate-sized databases. So what we constructed is we took an old construction for Oblivious RAM, which is called the square root solution, and we came up with a new modification on this solution. In our new construction, maybe can be described as a hybrid that leverages some ideas from the square root ORAM and some ideas from these tree-based ORAMs to achieve some better concrete efficiency. So as a result of this, our construction still has a asymptotic complexity that's square root, which is the same as the starting square root solution. And there are some inherent obstacles, which I'll try to mention why we were not able to get to the polylog. But for small to moderate database sizes, this solution has better concrete efficiency than even circuit ORAM, where circuit ORAM was tailored for the setting of secure computation. And in fact, it beats linear scan for databases as small as 8 elements, which suddenly brings ORAM and makes it applicable to much smaller database sizes. And then we implemented these algorithms and evaluated the performance with various algorithms that have been used before for evaluating ORAM, including binary search, breadth-first search, stable matching, and the script hash function. OK, so let's now go and see how we construct this solution. I think one of the features of this talk is that the constructions are kind of relatively simple to follow. So hopefully, I will be able to give you all the details of the constructions. So before we start with our construction, let me remind you or introduce to you the square root solution of Goldreich and Ostrovsky. So again, let me remind you, the goal is to construct a solution that stores data into memory, access it in sublinear time, and hides the access pattern. So the memory structure that the square root ORAM uses consists of a stash or shelter, which is of size square root of n. So everywhere n here will mean the size of our database. And then in addition to the stash, we have this permuted memory, which will be of size n plus square root of n. And these two, the stash and the permuted memory, will be the location where we will be placing our database. So our database will contain x1 to xn. Then we will generate square root of n dummy items. So these dummy items will be helping us hide access patterns. So once we have this n plus square root of n items, we will be permuting them at random inside this permuted memory. The way this was described in the square root ORAM was that you come up with a pseudorandom function. So pseudorandom function, for those who don't know, is a function that is a keyed function. and has the property that its output is indistinguishable from a truly random sequence. So we come up with a PRF function, and based on this PRF function, we compute tags for the items, and then we sort the items according to their tags. And this gives you the permutation that determines how to put these items in the main memory. So now we have placed our data in the memory. For all my talk, everything that sits in these memories, you can think of it that it's encrypted. So nothing from the point of view of reading what's stored in this location is leaked to the server who holds the database. So really, the only thing that we care about here is hiding access patterns. Privacy of the data is already handled by encryption. So how do we access something in this data structure? So if we want to access the data at location I in the original database, what we do is we first scan the whole stash. We check with linear scan of this square root of n items whether what we're looking for is already there. If we haven't found it in the stash, then we apply this permutation that tells us how items are stored in the main memory, and we look up that location. So we evaluate pi of I, if and only if we haven't found it already in the stash, and we look up at pi of I. However, and just a side note, if you're using this construction with the PRF, what you really need to do is a binary search on this permuted memory, but this is not a problem because these values, the outputs of the PRFs is public values. So doing the binary search does not leak anything more. However, if we have already found the item in the stash, then we look up one of these dummy items. So we keep a counter of how many items we have already visited, and we just look up the ith dummy item. And then after this, what we do is we add the item that we have retrieved from main memory to the stash. So why is this access pattern hiding? Well, this protocol guarantees that you will access a position in the main permuted memory only once. Because the second time you're looking for this item, you are guaranteed that you will find it in the stash, and you will choose a new dummy item, which will lead you to a different location in the main memory. So you will never repeat and access the same location in the main permuted memory more than once. So this guarantees to you that you will never incur this access pattern is only revealing something to you if you repeatedly access the same location. As long as you guarantee that each location is touched at most only once, and you have applied this permutation in the beginning, you are achieving this access pattern hiding property. OK, so far so good. But this stash is going to get full, right? So after square root of n accesses, it's going to get full. So what do we do after this? We need to shuffle back these items. We need to go back to the initial step where we put all the items together, and we permute them and initialize the main memory while emptying the stash. This is not so cheap in secure computation. In particular, if you want to do this as a two-party computation, you need first to do oblivious sort to remove all the dummy items, both from the stash and the permuted memory, because you don't know which ones of them are dummy. And you might have up to 2 square root of n minus 1 dummy items. And you need only square root of n if you want to initialize the main memory. So you do an oblivious sort to push them out. And then you're ready to repeat the initialization step. As a result of this, the amortized access for a square root ORAM that counts the initialization and the accesses is O of square root of n times log n. So I already started mentioning that there are some MPC bottlenecks when you try to use this solution. Just a reminder, when we use ORAM in the context of MPC, every of these operations, the access, the shuffles, the permutations in the beginning, will have to be executed as a two-party computation that has this representation as circuits and so on and so forth. So one of the most expensive steps in this protocol will be the evaluation of the pseudorandom function. A pseudorandom function described as a circuit is quite expensive, and in the two-party setting, your PRF key needs to be shared between the two parties. The other expensive step are these oblivious sorts that you need to do all over the place. So these were the two targets that we had in order that we wanted to optimize in our construction. So in our construction, we start with some simple modifications. First, we don't need to keep a stash that's of size square root of n all the time. We will increase the stash with the number of accesses. In particular, after t accesses, we only need a stash of size t. So we will incrementally be increasing the size of the stash, and this means that you will scan smaller stash at each access. Also, we would like to get rid of these dummy items. We don't want to have to deal with them. So we want to have a main memory that's only proportional to the size of our data. But then I need to tell you what you are going to do when you find the item in the stash, right? In order to preserve obliviousness, I have to give you an alternative. Well, the alternative will be kind of simple as well. Just access a random item that's still in main memory. And you can bring it up to the stash. That's OK. The next time you're looking up this item, you will find it in the stash. And everything seems to work. In addition to this, we will introduce another structure, which we call used items. And what we are going to store in this structure, oh, I don't have it here, but we will be storing the location in the main memory of an item that was moved to the stash. This is not revealing any additional information. For example, I see that I took the last item from the permuted memory, and I am moving it to the stash, so I just will store the last location in this used items array. And it will become apparent why this will be useful for us to keep this information later. In order to initialize our permuted memory, we will use a permutation, not a PRF, not a pseudorandom function. Now, this will create a lot of other questions about how you are going to share this permutation between the two parties. I will show you how we'll deal with this later. But for now, just think about that the two parties come up with a shared permutation, and they permute all the data for the main memory. And the access is pretty much the same as before. We scan the stash. If we didn't find it, we look up at the correct location in the permuted memory. Otherwise, we used a random index of items that have not been looked up already. We can find this using these locations in the array used. And then when we are moving the item to the stash, the item that we looked up from the main permuted memory, we also store its address in the array with used items. When the stash is full and it's time to shuffle again the array, what we are going to do is we will first write all the items from the stash back to the permuted memory. And we know where exactly to write them, because this is the information we have stored in the used items. So now we don't have this issue of trying to push out dummy items using these expensive oblivious sorts. So now we can just place them back where they were, and we can shuffle. So that's what we do. And then we just reshuffle the permuted memory. So this saved us a lot of expensive oblivious sorts. With this simple protocol so far, you're getting better efficiency than linear scan, even if your database is only 4 items. And here I'm not talking asymptotic. I mean, asymptotic, yes, as well, but even for actual numbers. So this simple modification is already giving you, in practice, improvement. OK, so now it's time for me to tell you what are we doing with this permutation. I told you that I'm not going to use a pseudorandom function in order to determine the locations of these items into the array. But pseudorandom function had a nice property that it has a short key. This short key can be shared, and the parties will hold it, and that's it. Now this permutation, how are we going to store it efficiently? Well, we are going to look at its position map. So position map is a term that comes from the tree-based constructions. So we just look at these pairs that tell you where each of the items is supposed to go. Then we will store this information recursively, which is what's happening in all of the 3 ORAM constructions. So what does this mean is that we take these pairs, we pack several of them, and we call them a new item. So now we get at least maybe twice as few items. Maybe you have a larger compaction rate. And now we take these items and we store them recursively in another ORAM. This ORAM will be smaller, will be at most half of the size of the previous ORAM. So this is how we are going to store the information about the permutation we used to permute our data into the main memory. And once I did it, I can do it recursively. And we were really hoping that because in the tree-based ORAMs, you manage to get to polylog efficiency, we will also manage to get to polylog here. Unfortunately, this wasn't the case. And the reason is that if you do the calculations, if you want to do t accesses in a particular ORAM, you have to pay t plus n accesses into your position map, where the little n comes from the fact that you need n accesses to initialize your position map in the beginning if you want to count the initialization. So now if you compute the amortized time per access, you can come up with a formula, and this formula gives you, with a little bit of computation, that your complexity is not going to improve from square root of n. At least with this approach, the way we are doing it, you're not going to get better than square root of n. So once we saw that we are stuck at square root of n, we decided that we are not going to bother to go all the way to log n recursive steps. We are going to stop as soon as the size of the remaining items for the smaller ORAMs becomes square root of n log n. So we wanted to save some unnecessary recursive calls and do just linear scan on the smallest one. OK, so what now the construction looks like is we have one more modification. In particular, the modification that we make the sizes of the stashes in all of the recursive instantiations of the ORAM construction to be of the same size. So in general, the smaller ORAMs were supposed to get smaller stashes. But we will use this property that they're of the same size in the next slide when I will tell you how to deal with the dummy items. I haven't told you how to deal with the dummy items so far. I mean, not the dummy items, but the dummy accesses, really. So what the construction looks like is you have these recursive steps that stop once you reach this size of square root of n log n. The smallest one is just accessed using linear scan. For all the rest of them, we have the same stash size. And when we want to initialize the position map, we don't really insert each of the blocks of the position map in the smaller ORAM. We just do one oblivious permutation to initialize the smaller ORAM. OK, so I told you that the reason that the sizes of these stashes are kept the same is because of these dummy lookups. What did I tell you we will do with the dummy lookups before? Because we no longer have these dummy items, we are forced to select one of the unused items. However, these, when we need to do it as two-party computation, you have several options. So you need to do this obliviously, because the parties, neither of the parties should know what items have been accessed already. So you can try to run some complicated protocol among them to determine which ones are still in the main unpermuted memory, but you run some problems of getting very bad efficiency there. What we will do is we will use this property that we kind of synchronize the shuffle steps for all the ORAMs. And in particular, we will have the property that if an item has been moved from the permuted memory or the shuffle to the stash in particular ORAM n, then we are guaranteed that the item that contains its position map in the smaller ORAM also has been moved from the permuted memory to the stash. So how are we going to use, and why is this true? Well, if we wanted to access an item here, we know that once we access it from the permuted memory, we move it to the stash. But in order to access it into permuted memory, we had to know which location in the permuted memory. The location is given by this permutation, which is recursively stored in the smaller ORAM. So we need to make a lookup for the position, for the item in the position map in the smaller ORAM. But once we access this item will also be moved to the stash in the smaller ORAM. So now we have this property that if you are moved to the stash, your position map has been moved to the stash in the smaller ORAM as well. So this property, we will leverage this property to do this, this random sampling a random element when we need to do a dummy access. So how is this going to work? So now we have the property that if we select a position map that's stored in the permuted memory in a particular ORAM, we are guaranteed that all of the items in that are pointed to by this position map will also be in the main permuted memory of the larger ORAM. So how are we going to do this? To do a dummy lookup, we will linearly scan the smaller ORAM, the smallest ORAM. We will select the first unused element. Since we are doing linear scan, this is trivial. So for example, this is the first unused element. Then this is guaranteed, this element is guaranteed that it's going to sit in the main permuted memory here. So we will find the item in that permuted memory. It packs a bunch of position maps. We will select one of them. This is again guaranteed to sit in the main permuted memory. And we will just keep on going in this way. And this property was enabled by the fact that we synchronized the stash sizes across all of the ORAMs. OK, so this basically tells you what were all of the steps in our construction. Now, in order to create the position map, we kind of came up with some protocols for doing this in two-party computation. So in particular, if you want to shuffle an array, if you want to generate a random permutation between the two parties, one approach is to use this Waxman permutation network, which is usually the fast way to implement shuffles in MPC. But when you want to share this, what you need to share is these control bits. But sharing just the control bits doesn't really give you a good way to share the permutation. So trying to go inside a particular permutation description and figure out how to share it between two parties doesn't seem like a good idea. But what you can do is you can just apply two independent permutations from each of the parties. And then the composition will be permutation. This will be the two shares of the composed permutation. So this is effectively the efficient way to permute an array in a shared fashion. So in order to compute the position map, so this position map is really given by the inverse of the permutation. So it's easy if the data is sorted. You can kind of run backwards your permutation network. However, if the data is already shuffled, which will happen in subsequent rounds when you need to reinitialize the ORAM, this becomes a little bit more complicated. One option is to first unshuffle, undo the previous permutation, and then start doing a new permutation freshly. This is a complicated method. Instead of this, we opted out to store, along with the data, the information for its position map. So essentially, to compute this information, we needed to give you a way to efficiently compute the inverse of a permutation, where originally the permutation was shared. And for this, we also came up with a protocol how to invert a permutation. So now our way of shuffling a particular array was to start with the array, apply one of the permutations coming from Bob. Then we'll reveal to Alice this composition of Bob permutation with the original permutation we are trying to invert. And now in order to compute the invert permutation, we will compose the permutation of Bob together with the inverse of the permutation that Alice can compute in the clear. So once Alice has computed this in the clear, the composition of pi sub b and pi inverse of a will be done in secure computation. Like Bob will apply his permutation, Alice will apply the inverse of her pi sub a, and this will result in applying the inverse permutation on the original data. So again, computing the inverse permutation, you will not need to do any expensive computation inside of a circuit, but rather you will ask each of the parties to apply two permutations that they have in the clear on a data that's given to them and it's already shuffled. OK, so these are kind of, if you're interested and you need to do shared permutations, which are all over the place in MPC, you can look up the protocol. I also have this nice figure, which I don't know how much you see from the figure, but it essentially describes the flow of accesses into this ORAM, where you have this, here in this particular example, I have these 3 levels of recursive ORAM. And here we have shuffled the data. We have initialized its position map. So this little thing means that in this item, in the 0th item in the position map, I store the locations of 0 and 1 in the main ORAM. So now if I want to do a lookup, what I have to do in the beginning is I look at the stash here, it's empty. Then I go and I look at the stash here, it's empty. So I end up going to the smallest one. From the smallest one, I retrieve the position map for the element in the previous level. I open the position map. I find the pointer for my specific element, and I go to the ORAM above. Now, in this second lookup, the second lookup is showing us a case where we find already the item that we are looking for in one of the intermediate stashes. And then we will need to do these dummy lookups in the smaller ORAM that I was talking about. So since I'm running short on time, I'm not going to go through the exercise of following all the arrows. But if you're interested and you found the description of the construction complicated, even though it's very simple, if you know the square root ORAM, you can look at this example in the paper, and hopefully you can recover it on your own. So now that we had this construction, we implemented it and evaluated it. For this, we used several Amazon EC2 servers. To be fair comparison, we first re-implemented circuit ORAM with all the optimizations that we have developed already. We applied them first on the circuit ORAM so that we can give it the best chance to give best performance. This was related about how we shuffle things, about how we pack in this recursive instantiation of the construction. And then for our micro benchmarks, we had a comparison with circuit ORAM, or the best variant of circuit ORAM that we had. and and also with linear scan, which is the trivial solution. And we were evaluating both the access time as well as the initialization time for all of these ORAMs. And also we looked at several applications and what is their computational complexity and efficiency when we evaluate them using our new ORAM. So what this figure tells us is for what sizes of databases, where this is the number of blocks in the database, and this is the size of each block, what ORAM you should use. So if you're in this region, linear scan is still the fastest. If you are in this region, suddenly you have a better alternative than linear scan. So before our work, up to here, everything was linear scan. You had to use linear scan if you want to be the most efficient. You want the best practical efficiency. Now, our square root ORAM is the fastest existing ORAM if you are within these database sizes. And these database sizes cover quite a large range where many practical databases might fall in this range. If you really go to large databases, circuit ORAM is the best one because asymptotically is still the best one. Circuit ORAM is polylog. We are still square root of n asymptotically. If you want to look at different way of intersecting all of these solutions, and you're looking at the running time for an access, which includes initialization, again, this gives you the intersection points of up to where linear scan goes, then there is square root ORAM, and then we go to circuit ORAM. These lines, the solid line is if the block size is 16. The dotted line is if the block size is 32 bytes. We also looked only at initialization cost. So this is only initialization cost across the different constructions. And linear scan, the initialization is essentially doing a permutation. Or not even doing permutation, just sharing the data between the two parties. And then we have a square root ORAM, which has faster initialization than circuit ORAM for most of the sizes. So here I also have some particular timings. If you do binary search, so we do it 2 to the, this is the times for if you want to do 2 to the n searches on a database of 2 to the 15 elements. So this is the total time you get with the different options: linear scan, circuit ORAM, or square root ORAM. We also did breadth first search, and in breadth first search, this was the size of the graph. We had 2 to the 13 edges and 2 to the 10 vertices. So again, our square root ORAM for this specific application outperforms both other options. And then in stable matching, I think linear scan was not even possible to run. I think it was so expensive that we couldn't run it. Script really pushed the boundaries of linear scan, so we had to run it for 7 days. So script is this hash function that is meant to reduce the possibility of parallelization. We just had, I think, an implementation of this script, and we decided it's a good example to try it on. And again, here, square root ORAM outperforms the other two options. So in conclusion, for this work, what I can say is that here we propose a new construction for square root ORAM that kind of brings together hybrid techniques from the tree-based ORAMs and the hierarchical-based ORAMs. It improves the initialization cost, which is this preprocessing step for all the ORAMs, and also improves on the break-even point against linear scan and against circuit ORAM as well. This also tells us that if we want to use ORAM in practice, asymptotic costs are not the final word. We really want to see what are the concrete constants that all of these constructions have, and we gave a way to like push the boundary where ORAMs are applicable for much smaller database sizes. One open question here that still remains is, can we get to polylogarithmic complexity? And this construction we didn't manage. We had to stay stuck in square root of n, but maybe there are other ways to extend this construction since we know that this recursive approach in the tree-based ORAMs manages to get to square root, to polylog. Here, one of the things that was making us pay a high cost is that we still had these steps where we needed to do permutations, like these expensive steps that could not be deamortized. Somehow the tree-based constructions have a way to deamortize the cost again across all of the accesses. So you are at the same time slowly shuffling the database. When you have this approach, our approach, similarly to the square root ORAM, we had to do these permutations all at once. So this was also coming as a penalty for the cost. And I think I have 1 hour, right? So I think in the interest of time, I'm going to skip the other work that I mentioned in the beginning. If you are interested in learning about the other work, I can tell you in more detail. But I think otherwise, I will just end up rushing through some definitions, which will not be so useful.